Hi, today I talk about differential pressure volumetric flow rate. Volumetric flow rate are used to decide the volume of material that flowed during a specific period of time. Unit is just cubic feet or gallons or liters / second, minute, hours. In many situations, volumetric flow rate is not measured directly. Instead, an infrared measure is taken. What means infrared? Infrared means some other variable is measured, then translated into the reading that is required. So, a lot of instrumentation devices use infrared measurement. Okay, so volumetric flow rate its formula is Q equal V times A. Q is the volumetric flow rate. V is the velocity of the flow. A is the cross-section area of the pipe. So, how to get the Q equal VA? Let me discuss. Okay, we know all the flow rate is Q equal volume divided time. So volume equal area times length. So Q equal area times length divided time. So velocity equal length to time. So Q equal VA. Okay. So V is the velocity equal length to time. Length to time is error. Error is error. Okay. Here the cylinder, you can know how to this error. This cylinder look like a pipe. Okay. It's a pipe flow principle. Pipe flow principle have 4 parameters. One is the velocity. Second one is the density. Third one viscosity. Last one is pipe size. Velocity just is speed. If the faster the flow is flowing, the more initial it has. Density. The density of flow is weight per unit of volume. Both temperature and pressure affect the density of fluid. Viscosity. Viscosity of a fluid represents the ease with which it flows. Its high number viscosity means it's not moving fast, it's moving slowly. Don't want to move it, but it's called viscosity. Pipe size. Pipe size, just the size of the pipe carrying a fluid affects the diameter of the pipe. The more easy flow was pass. Okay. Temperature and the pressure still affect the viscosity, same as the density. Okay. Is the temperature too high? Is the viscosity is too low? Is the pressure too high? Viscosity is too high. Okay. It's Reynolds number. What means Reynolds number? Reynolds number just represent the flow. It's the behavior. So Reynolds number equal dVp divided by U. V is the velocity. D is the pipe inside diameter. R is the Reynolds number. P is the fluid density. Sometimes we call ρ. Yeah. U is the liquid viscosity. Okay. Viscosity is too high, is ρ is too low. Okay. So It have three candle number represent the flowed behavior. Okay, one is nominal, second one transition, third one turbulent. The nominal is flow velocity near the center of the pipe is greater than the pipe wall. Here is speed and the velocity is too high, but near the pipe wall is too low. This is called nominal. Its raw R number is less than 2000. So is here is too small. That means its viscosity is too high. Its viscosity too high is moving slowly. Okay, transition flow. The nominal flow became non-symmetric. Its R number is 3000 to 7000. Third one is turbulent. Turbulent is flow look like here. Is no former is uniformly break up, developing into the turbulent eddies that travel in all directions in the flow stream. The R number is 7000 to 8000. These three correct nominal, transition, and turbulent just describe the volumetric flow rate, the behavior. Okay, the differential pressure flow meter, the most common type of instrumentation used to measure the flow of fluid through a pipe. All flow over 50% measure device used in the process industry. That's mean over 50% measure flow rod use the different pressure transmitter. Okay, it use restricted to the flow to measure the flow rate. Here, according to the law of conservation of energy, the mass is flow enter the pipe must equal the mass leave the pipe during the same time period. From here going in equals from here go out. That's mean Q equal A1 times V equal A2 times V2. Okay, here the flow rate equal here the flow rate. Okay, 0.1 equal 0.2. The Bologna principle. This one is thermodynamic. It's the principle. Okay, in fluid dynamic, an increase in the speed of fluid occur simultaneously with a decrease in pressure or decrease in the fluid potential energy. What's mean? If your speed too fast, the pressure to decrease. If your speed too slow, the pressure increased. Okay, here is the Bologna principle. Here is the pressure energy, kinetic energy, energy and the potential energy equal. The second phase is everything. Okay, here we can use. In here, look V1, P1, A2, V2, P2. Which one is larger than other one? Let me see. Here, phase 1 here is area is large. Area is large, is velocity is slow. Is velocity slow, is pressure too high. So is A A1 larger than A2, but V1 smaller than V2. but on the P1 crash in the phase in here, point 1 is the large P2, okay, in here. A1, large A2, V2, large then V1. So P1, large to P2, yeah. Area large, ratio is go down, decrease. Is A1 increase, velocity is go decrease. If velocity is decrease, pressure increase, okay? Just follow this formula. A1 times V1 equal A2 times V2. So here is the three different type of flow restriction used to convert pressure differential into the flow measurement. First one is orifice. Second one is flow lossy. Third one ventured tuber. All these three kinds is very popular in the industrial area fields. It's different, is orifice, different pressure transmitter. It's the flow nozzle, different pressure transmitter. Venture tuber, different pressure transmitter. Okay, it's the Bolland principle. Okay, here we talk. Here, Bernoulli equation. How to, if your Bernoulli equation in here, we know this one. Okay, Bernoulli equation. Your Bernoulli equation, we can change something. We can go to this one. If you're just a little bit changing, we go to V2. Then bring V2, go to there. We go to volumetric flow rate. Is Q equal K square root P1 minus P2 divided the rho. Rho is the densities. Is P1, P2 is the pressure. Is the K is a constant. Okay? K is a constant of proportional as a unit of measurement correction factor and decided by physical experiment. If you designed something, is for example, is pipe designed, is everything that designed, you use orifice or use flow nozzle and virtual tuber. After that, you can go to the K constant. Okay, so different pressure flow rate method is Q equal K square root delta P. Q is volumetric flow rate. K is constant of the pipe and liquid type. Delta P is the differential pressure drop across the restriction. This formula we often use to decide its flow rate, volumetric flow rate. Okay, but we just use in the transmitter. We often use this formula to decide which flow rate. Okay, so we follow this formula. We can go to this curve. Is a flow element function, square root function. That's me. You can see this not linear is curved. Okay, so that means the differential pressure flow rate is not linearity with the different pressure. So it's not linear. If you're not linear, so we should use other device to keep this output is linear with input. We use square root extract. In traditional DP transmitter, is analog signal, square root extract device was required. Okay, this is called square root extract. This square root extract inside, okay, is components. But now in the modern smart transmitter, all the transmitter have the square root extractor calculation. So no, most time we never see this one. Okay. Here, look. Here's different pressure instrumentation, collection, square root extractor, then collection indicate gauge. Okay. Here, look the orifice, the different pressure transmitter. Okay. Here is the sensor. Here is the sensor. Here is the different pressure. Here is the pressure higher than this pressure. Okay. Here the error is large. Then here error is large, but the velocity is low, is small. So pressure is too high. Okay. Here pressure too low. Okay. After square root extractor, the signal became linear, became linear. Okay. The pneumatic square root relay. So this for pneumatic square root relay. If you're 3 psi after square root, it's the 3, oh, this one doesn't matter, don't change. Just 4 psi, it becomes 6 point psi. It's 7 psi, it become 9 psi. So not linear. It's not a linear relative line. Okay. So different pressure. The square root is 4 to 20 MA. It's 4 MA. It's 25 MA should 8 MA, but here is 12 MA. Or 50% is 12 MA, is 15 MA. So all of it is the square root. Not the square root extract, just the square root. Okay. So square root extraction enable accurate flow measurement by establish a linear relationship between the square root of different pressure and the flow rate. So just the square root is the purpose, just the square root extract the purpose. Just make is non-linear curve become a linear curve. That's it. It's an input output, it's not no linearity. But after square root extractor, it became is input output is the linearity. Okay, look like this. The linear relationship facility accurate flow rate measurement, increase instrumentation rangeability, and improve the losing immunity. Okay, so almost modern smart different pressure transmitter allows the dP to square root convention to be calculated with the transmitter. That means we don't now we always use smart transmitter, so we don't worry about square root extract. He just the calculation on the convention already in the transmitter. But all the SCADA and the DCS system have inbuilt square root extraction function block to configure input from DP transmitter. All the square root extraction are performed in one or other of these locations. That's mean if you know transmitter, if you don't have the square root is calculation, so you just do just one maybe DCS, maybe SCADA, or maybe in the transmitter, or sometimes just the controller. Okay, so the instrumentation and the control system have an option for where to have the signal conversion. Okay, where you should decide where you should do square root conversion. But now the modern smart transmitter, all the stuff just needs the in the transmitter have including square root convention, so you don't worry about this one. Okay, today we just talk about square root, the volume flow rule. Okay, thank you very much.